We're going to compare proportional relationships given in different forms. In this example, we can see that we have three airplanes, A, B, and C, and we have three different forms of the same type of information. The first one being a graph right here, the second one being our equation right here, and the third one being a table right here. Now, when we talk about proportional relationships, what we want to try to do is get down to a unit rate if possible. And when we talk about unit rates, we're asking, how does our x value, or in this case our time, affect our y value? And again, in this case, our distance. And we can see that we have the same information across the board for all three examples. How does our time affect our distance? And in this one again, how does our time affect our distance? So that's what we're looking for here, is how does time affect distance? Well, in a proportional relationship, we can write this equation as y equals kx, where k is our constant rate of change. X and y then are the input and output coordinates that will allow us to graph or decipher the equation or the table. When we look at this, if we want to know what our constant rate of change is, well, we could divide both sides by x. And when we do that, our x's will simplify to 1 right here, and we end up with the constant rate of change being equal to y over x. Now, if we just apply that information to airplanes A, B, and C, we'll be able to answer part A, B, and C of the ALEKS question here. So with our first one, this is airplane A. So we'll say air A. And if we want y over x, then we can come to our graph and say, well, I see 0, 0, and of course I never want a fraction or a ratio with a denominator of 0. So I'm going to move on. I'm going to find a different point. I see that there's another point right here on the graph at y equals 600, x equals 1. So I can say y is 600 and x equals 1. Excuse me, that is x equals 1. There we go. And the reason I want to try to get it to a unit rate of 1 in my denominator is so that I'll be able to better compare all three airplanes. All right, let's look at airplane B now. Air B. And airplane B, we can see that, again, if we line up this equation they've given us to our original equation, y equals kx, we can see that distance equals 580 t. And we know, since we know that our x value is our time, we can now fill this in. So y is our distance, x is our time, and when we look at this, we can line these up, and we can see that if I were to put in a time of 1, which would be my denominator, then 580 times 1 would give me 580 as my distance or my y variable. So I now can fill this in with 580 for y. And finally, we're going to compare airplane C, air C, and again, still in y to x. And as I look at that, this one, I can see that since I know my time is my x, the same as in my airplane B and airplane A scenarios, and again, I don't want 0 in a denominator, I can go straight to 1 on the table for my time, and I can see that that corresponds to 610 for my y, or my distance. Now I can compare all three of these. So my meters per second, meters being my distance, per second being my time, meters per second, and meters per second. I'm just going to fill these in. 600 to 1, or just 600 meters per second. Now, ALEKS may or may not want 1 as a denominator, and if that's the case, just put in 600, and that will work as well. Airplane B, we've already discovered, is 580 meters per second, and airplane C gave us 610 meters per second. So which airplane is the fastest? Well, the fastest would be the one that can go the farthest in that same 1 second. And so we can find that airplane C is the fastest at 610. And finally, how far does each airplane travel in 2 seconds? Well, 2 seconds, twice as many as 1 second. I could use my equation up here to plug in 2 instead of 1, and then I could do the math and find out that that would be, let's see, 1160. So I know that that is there. Or I can just recognize that 2 is twice as many as 1 and double all of my distances. So how far will airplane A go in 2 seconds? It will go 1,200 meters, twice 600. Airplane B will go the 1160, as I proved in my equation when I plugged in 2 seconds for time. And airplane C, I can double that, or I can look at my table and tell you that it goes 1220. To back up just for 1 second, airplane A, I could also look at my graph and figure out 2 seconds, 1,200 there. So a way to use all three of them to double the amount of time with 2 seconds. And this would work the same way for 3 seconds, 4 seconds, 5 seconds, 10 seconds, any amount of time as long as it's in seconds.